Hey everyone, Mr. Kimson here, and today we're going to be learning about something called the Bernoulli Distribution. And so essentially this topic is related to probability. Now, when you think of probability, you might think about things like, oh, what's the chance that I take a red marble out of this bag? Or, what's the chance that I win this particular lottery ticket or something like that. And while we will certainly look at examples which represent these situations, what we want to try and do in this topic now is move away from just looking at probability as a topic by itself and see how it actually relates to what we already know about functions and in particular discrete probability functions that we looked at back in year 11 advanced. So that's just a bit of a taste of what we can look at. Before we jump into the topic, I do want to just define some things first. So the difference between what we call a Bernoulli distribution and a Bernoulli random variable is how I like to think about it is a Bernoulli random variable is sort of an instance of this situation that we look at. So what kind of situation we're looking at? Something that has two outcomes, success and failure. Now this over here is sort of a mathematical way of representing them, and typically, we define 0 as being failure and 1 as being success. So what kind of situation only has two outcomes? The easiest thing to think of is, for example, flipping a coin, right? When you flip a coin, you get heads or tails. Now that has two outcomes, but we have to be particular about this language here. And when we talk about success and failure, we have to phrase the random variable in such a way that success and failure make sense. In heads or tails, it's not necessarily clear what's a success or failure. For example, if I flip it and no one calls for it, whichever one they want, then there is no success or failure, right? So what we do is, and this is how we phrase these random variables, so to speak. Let's have a look at this one. So some examples of this: tossing a tail on a coin. So you can see how they specifically refer to the term tail. So the success would be getting a tail, or the failure would be not getting a tail. And I've just been pretty clear with how I put the language in the brackets. So tail or no tail. A tennis player will win a match, win or no win. Recently, Novak Djokovic won the Wimbledon Grand Slam, and so that's pushed him up to now 20 titles, which rivals Rafael Nadal and Roger Federer, the GOAT. But I guess that begs the question, what was the probability that he would win that particular match, or in the future that he'll win more matches as well? This is what a Bernoulli random variable and ultimately a Bernoulli distribution will try and answer this kind of question. Some more examples: choosing a red snake from a bag. And so notice here, the bag actually contains many other colors, but because of the way in which we phrase the question, a random variable, red or not red, this is still meeting that criteria. So only having two outcomes, success or failure, right? Whether or not you'll get a job you apply for. So, you can receive an offer, you're accepted, or you don't receive an offer, you're rejected, unfortunately. And there's actually a pretty interesting article that I'll link below that looks at how many times, using this idea of a Bernoulli distribution, how many times you have to apply for jobs until you have a certain level of percentage of success. That's basically what these sort of situations are looking to do here. But we'll get into that in a bit, right? Things which are not examples. So things that aren't Bernoulli random variables, so the number rolled on a die, right? So you can see how there's no real clear success or failure there, right? It's just 1, 2, 3, 5, 6. Number of goals in a hockey match, same idea, right? There's any number can happen. We need two things: success and failure. That being said, though, that doesn't mean that these situations can't be written in such a way which they are Bernoulli random variables, right? So look at the die situation again. Construct a discrete probability distribution table and bar graph for rolling a 6 on a die. So remember how I said there's success and failure? Basically, you have two outcomes here. The success would be rolling a 6, and the failure is not rolling a 6, right? So what does it mean to construct a discrete probability distribution table and a bar graph? Well, essentially, when we look at representing these Bernoulli random variables, there are many different ways we can do it. A table is a common way, right? So when you think about a table, think about a few things. First of all, what are the outcomes that you can get? The outcomes in a Bernoulli random variable, there's only two things. You can either have success or failure, and represent that using 1 or 0. So that's the first thing I want to put in. So the first thing we put in is, okay, this is our sort of score, and so we can either get 0 or 1. I remember what that represents. It represents success and failure. What is the failure? Not rolling a 6, right? So what's the probability, the chance that it occurs? Well, that's 5 on 6. And the chance that I get a success, the chance that I roll a 6, that's 1 on 6. Now, the notation for the probability, if you remember back again from the discrete topic, looks something like this, right? This is just basically saying what's the chance of the probability of these particular outcomes, right? So that's the probability distribution table. What about this bar graph? Well, similar idea. If I want to draw a bar graph for this, let's just draw my axes first. And remember, we have two outcomes, right? We can either get 0 or 1. And then what's the probabilities of these going to be? Well, it's either going to be 5 on 6 or 1 on 6. I'll put that over here. So it looks something like this. And of course you would use a ruler, which I would if I could. Okay. And so that's what a bar graph and a discrete probability distribution table might look like. And we should probably label our axes as well. Hey, okay. Cool. Awesome. All right. So what other questions can we answer? Well, before we look at some more complex situations, I want to sort of more formally define what I mean by a Bernoulli distribution. So I've been talking about these random variables as like a single instance. But what we sort of started constructing now is this distribution, so a mathematical representation. And so this is sort of the formal definition. We can see that notation there. Remember, this is sort of saying that the probability that something occurs. And we look at over here, x equals to 1 and x equals to 0. So remember, we're talking about here success and failure, right? And so the probability for that particular success, P, that's the probability that we get a success. And so naturally with the complementary rule, 1 minus P, that's the chance for failure, because those are the only two things that can happen. Again, visually, this is what it might look like. This is if the chance for success is 0.6. You can see it goes up to here. But then failure would be 0.4, so adds up to 1. Here's a similar idea as well. We've got 70% for failure, and so you've got 30% for success. That's what these distributions might look like. There's other representations too, though. So they want us to write a Bernoulli distribution for the following situations. For example, flipping heads on a coin. Right? So what might that look like? Well, again, you've got your probability of success being half, and then the probability of failure, that's 1 minus P. Sometimes they'll say that that's Q, but 1 minus P, that's just half as well, right? And so if I want to draw up my probability distribution, I can use that table, I can use this graph, but I'm going to use this definition here that they've done. So, okay, so I'll write it out like that. Okay, so there's my probability distribution. I've got the notation, I've got the curly brackets. It's half for x equals to 1, flipping heads, half for x equals 0, not flipping heads, right? That's essentially what this is saying. Okay, what about this situation? Passing a test where the success is 33%. So what they mean is the success in passing, essentially. Which you may think, that seems a bit low. In actuality, this is based off, and I was talking to someone I know who is an actuary, and it's a very prestigious job that they look at calculating risks, and it's quite technical, and so they need them to pass these exams. And actually, you can see that the pass rate has fluctuated over time. These are from the past couple of years up until 2018. and so maybe in some instances it's higher than, it doesn't go any higher than 45%, you can see there, but in some instances it's high, it's lower, it does fluctuate. I'm basing it off this 2018 result, which is approximately 33%, and so it's not too far-fetched that can be a pass rate, right? So 33%. So when I want to think about my probabilities, I've got my pass rate or my success being 33%, and then so 1 minus p, well, I'm taking that away from 100%, so I've got 67% here. And so now I can write up my distribution like so. Okay, so there's my probability distribution. So 33% for x equals to 1, 67% for x equals to 0. Last but not least, here's one for you to try. We've got selecting a ball where there are 7 red and 8 green balls. Right? So at this one, again, I want to think about, okay, what are the probabilities for success and failure? So selecting a red ball, well, that would be 7 out of the total number of balls, which is 15. And so 1 minus p is just going to be 8 out of 15. And I can draw up my probability distribution like so. Okay, so there's my probability distribution. So what have we looked at? We've looked at what really a Bernoulli random variable is. So it's this instance that we can sort of measure when there's a success and a failure. The distribution now is sort of representing that mathematically, either using this definition that we just did, or graphically, or in a table. And then after this, we'll look at some different problems.